Hello again, and welcome back to Statistics, where we're getting on to the last couple weeks of class. This week we're going to be looking at parts of Chapter 10 in your book, and Chapter 10 deals with the topic of what's called chi-square. Now, if you look at the symbol for chi-square, it looks like x squared, but this is the Greek letter chi, and something that's always been a pet peeve of mine is people that say that wrong. It is chi-square, it's not chai like expensive tea, it's not chi like the soul in Asia. It's chi-square, which is the name of the topic we're looking at. Chi-square is just another statistic, and it happens to be one of the most versatile statistics that there is. You can use it in totally different situations than you can things like T and Z and R that we've talked about already. And in fact, in the real world, chi-square is probably the most used statistic that there is. Your book makes a big deal of is that chi-square is a skewed distribution. That's not necessarily the most important thing, but it is a little bit different than Z and T because it doesn't make a mirror image. You don't have the same thing with positives and negatives like you do with the other statistics that we've looked at. On the other hand, what you're going to be doing as we go through this chapter is just looking at p-values again, and those work exactly the same as they did with T and Z. It also tells you here that there's a different chi-square distribution for every number of degrees of freedom. That's a term I haven't really talked about yet. Sometimes I'll bring that up when we do T because it also kind of works the same way, but with T it's just built into your calculator anyway. On chi-square, on one of the tests we'll do, it's going to ask you how many degrees of freedom there are, and I'll point that out when we get to it and how you do it. When I first learned about degrees of freedom, the instructor I had said you could think of it as if you were looking at one thing, how many other things in your group are you free to look at next? It always ends up being one less than something, and that's how we're going to end up dealing with it as we go through these problems. There are a ton of chi-square tests. We're going to actually look at two of them today, and there's really just one that you truly need to know inside and out. The other one you'll end up learning the basics of, but partially because it's not built into everyone's calculator, we're not going to have everybody do that test. The first one, though, you do need to know how to do. And that first one is what's called a matrix chi-square test. At least that's what I call the test. In your book, they refer to it as a test for independence. And on your calculator, it's just called chi-square test. And we're going to figure out how this works and what you do with it. What a chi-square test technically does is it compares two qualitative variables. Qualitative variables were ones that dealt with things rather than numbers, where you counted up how many there were of different things, as opposed to giving a score that you'd have with a quantitative variable. What we really do here is you answer the question, does the distribution of one variable change as you change the value of the other one? Now, I know that still doesn't really make a lot of sense to you, so I'm going to try and show you some examples and then sort of summarize how this would always work. I'll often have people do chi-square tests for their project, and a real common project people do involves colors of candies like M&Ms or Skittles or things like that. One question that this particular chi-square test could answer is whether those colors are distributed differently in big bags and little bags. You tend to get different colors if you have like the little snack size Halloween packs or if you buy the big pound bag that you can share. Another question you might use a matrix chi-square test for would be if you wanted to know whether different ethnic groups vote differently. Is the distribution of Republicans and Democrats different among white people, black people, Hispanic people, etc.? Yet another possibility would be whether people access the internet in different ways depending on their age. I'm an older person, and my bet is I'm much more likely to use a computer than a lot of you guys are who are watching this, and very likely are watching it on your phone. I think older people do tend to use computers more, and younger people are more likely to use their phones. The really important thing about a matrix chi-square test is it always involves some sort of a table. If you look through this section in the book, what they're going to tell you is that you can arrange your data in a contingency table. If you see a bunch of numbers that are all displayed in a table, in rows and columns, it's probably going to involve a chi-square test. A matrix is just a fancy word for a table, and that's why I tend to call this a matrix chi-square test, because we're actually going to use the matrix feature that's built into your calculator. I'm going to go through 3 examples to show you how these tests work, and the first one is just a bunch of made-up numbers. It says, suppose there's a TV class where we have students at all 5 Iowa Lake centers, and I have a table that shows you the distribution of them. Now I know, especially if you're watching this on your phone, it's probably hard to see those numbers, but there's just a bunch of numbers. It says in Algona there's 5 males and 7 females, Emmitsburg is 3 guys and 2 women, Esterville is 4 and 4, Spencer's 4 and 7, and Spirit Lake is 3 and 3. That's distributions that aren't that uncommon at the different centers in terms of how many males and females, although this is a way bigger class than most of the ones we have on campus these days. The question we're going to answer is whether the distribution of men and women varies significantly by center. Something that I've noticed as an instructor over time is that very often some centers tend to have more women than men, and some other centers tend to have more men than women. A lot of times, Emmitsburg in particular has more men than women. That's actually not true in my class this semester, but it often is. And a lot of times, Algona and Spencer, both of those, you tend to have a lot of nursing students, and those often end up being heavy on females. So you can end up with different distributions at the different centers. Another way to think about what we're looking at is as I go from one row of the table that I had there to another, is the distribution in the columns different? Is it different in Algona than it is in Emmitsburg, than it is in Esterville, than it is in Spirit Lake, and than it is in Spencer? If I get a significant result, I'm going to have a result that tells me that, yeah, the distribution is different as I go from center to center. If it's not a significant result, it would mean it's pretty close to the same, and whatever difference I have could easily just be by chance. The basic process that we're going to do is pretty much the same as what you did with Z and T. We're going to calculate a p-value. That's actually a little bit more involved than it was with Z and T, but it's not hard to do at all. Once I have a p-value, I'm going to compare that with the level of significance, and we'll figure out whether this is or isn't a significant result. You can calculate the p-value for a matrix chi-square test on basically any graphing calculator, and it's also built into things like Excel and other spreadsheet programs. You guys are typically going to use a TI-83 or 84, and to do that you need to find the test menu on your calculator. Now I want to point out that this looks just a little bit different depending on what calculator you have. If you have a TI-83, which is where most of the screenshots that I've shown you over the year come from, there's just one test that's called chi-square test. It happens to be choice C, and it's a little bit easier to get to it by scrolling up rather than down when you get into that test menu. If you have a TI-84, you're going to have more than one test that's called chi-square. The one you want is still choice C, the one that just says chi-square test. You don't want the one that has GOF. That's the other one I'm going to talk about, but the one that you don't actually have to do the test on. Now we'll get back to doing the test in a little bit, but first we need to do the preliminaries for it. Before you actually do the test, you have to take the table you were given and put those numbers into your calculator, because your calculator has to know what is the data that we have. To do that, we need to use the matrix mode on your calculator. And exactly how you get there depends on what your calculator says. Some calculators, especially older ones, will have a key that says matrix on it. A lot of times actually the I is missing and it just says matrix, but it's the same key. If yours has that key, great, you're going to press it. If it doesn't, what you're likely to have to do is press second and then the key that says X-1 over at the left-hand side. And on older calculators, you just press matrix, and if you have a newer calculator, typically it's the second key, and then right above X-1, you want to get into matrix mode. So one way or another, you have to find matrix mode. Once you get there, you'll see a screen that looks kind of like what's on the left. It may have some numbers after these names of matrices, it may not, but it doesn't matter. What you want to do is to use your arrow keys to go over and choose Edit. And we want to edit matrix A. To do that, you're just going to hit Enter. And again, you might have some numbers other than the 1 and 1 that are on my screenshot. Makes no difference what those numbers are because you're just going to type right over them anyway. And so you go into matrix mode, use your arrow keys to go over to Edit, and hit Enter to choose matrix A. The first thing you're going to be asked are the dimensions or the size of this matrix. It's asking you how many rows and how many columns there are. Rows, you always read across, so you count them by going down. And columns, you always read up and down, you count them by going across. The table that I had a minute ago, it had 5 rows for the 5 campuses and 2 columns for male and female. So what I'm going to do is hit 5, enter, 2, enter. So you put in the rows, press enter, put in the columns, press enter. And what happens when you do that is it sort of magically draws a picture of that size of a matrix on your calculator. Again, it might have some numbers in it, it might just have zeros in it when you do that. Once you've got those in there, what you're going to do is type in all the numbers in the matrix. Here's the matrix we were given again, and again you can see it's 5 rows and 2 columns. I do just look at the numbers, I don't count the titles when I do that. And what I'm going to do to type in the numbers is I just type 5, enter, 7, enter, 3, enter, 2, enter, 4, enter, 4, enter, 4, enter, 7, enter, 3, enter, 3, enter. I always go across and I make sure that I hit enter after every single number. It's probably most important that you hit enter after the very last number, which sometimes people forget, but you do want to make sure that you do hit enter at the very end. If you don't, it'll have whatever was there before and won't change it to your new number. If you look at what's on the screen now, you can see it's exactly those numbers that were in the table I gave you, 5, 7, 3, 2, 4, 4, 4, 7, 3, 3. All of those numbers are in there. Sometimes it's not a bad idea to make a quick check and make sure you typed everything right. This is though, so yeah, I'm good to go. If you do have everything typed right, then probably the best thing to do is to hit second and mode to quit out of there and just go back to your main screen. You don't actually have to do that, but it keeps you from doing anything wrong, and that's not a bad thing to do. Now you will actually do the test. And so you want to go to Stat, Tests, and you want to choose chi-square test. Again, if you do have a TI-84, it's choice C. It's just the one that says chi-square test. You ignore the chi-square GOF that comes below that. Your calculator is going to say observed expected. You want to make sure that it does say matrix A next to observe and matrix B next to expected. Chances are it will. I think in all the years I've taught this class, I've had exactly one student whose calculator, for some reason, did not have the defaults on it. If yours doesn't, the way you would get them there is to go back to matrix and you choose names and just put the name of the one you have there. Honestly, if for some reason yours does have an issue, give me a call or an email and I'll get you back on the right track, but just check and make sure it says A and B. Some newer calculators may also have a choice that says color. If it does, you just ignore that. It doesn't matter. You want to go down to calculate and make sure calculate's highlighted and then hit enter. And it's going to give you a whole bunch of things on your screen when you do that, just like when we were doing Z and T tests, like what you did in your tests last week. All you really care about is the p-value. And so here it tells us that p is 0.91289637711. And again, just a couple decimal places is usually fine for that, so 0.91. We interpret this exactly the same way we did with Z and T. The p-value is the probability we're wrong if we say this is significant. And this is basically saying we're going to be wrong 91% of the time. That's way too often. And it's way more than what we would have for 10% that we're willing to accept. And so that is not a significant result. Again, I compare the p-value with that alpha, that level of significance that's given in the problem. You want it to be less, but here it's more. Something I'll just point out to you on the side is that chi-square tests will tend to have a very wide range of p-values. You can get things that are as big as that 0.91 that we just calculated, and you can get things that go into scientific notation, like some of those ones we did with Z and T. It's okay to get just about anything for a result. If you'd been doing like a z-test earlier and you'd gotten 0.91 for an answer, that usually means you typed something in wrong. On chi-square, yeah, that does happen. So, don't be afraid if you do get weird answers because big and small both can happen with chi-square. So here's another example. It says we're talking about the relationship between education and marital status, and we have a table here that's talking about whether people have middle school or lower education, high school education, a bachelor's degree, a master's degree, or a PhD or higher. And they have how many of those people were never married, married, divorced, widowed. So we have all of those different numbers that are there. Now, if you want to follow along with this, you might pause the video and start typing those numbers into the matrix. Honestly, though, it's probably just as easy on this one to follow along with what I'm doing. The question's asking us, is there a difference between marital status and different levels of education? And it tells us to use alpha equals 0.05. So if I get a p-value that's less than 0.05, it'll be significant. If it's more than 0.05, it won't be. My first step, again, is to go into matrix mode. And part of the reason I chose this example is that it had a bigger size of matrix. This one, we're going to end up with 4 rows and 5 columns, 4 marital statuses and 5 kinds of education. And so that's why in those first couple of spaces, I typed 4 and 5. 4 enter, 5 enter. And the matrix that it draws actually goes off the screen. You can't see all of the numbers on there. That's okay. I'm still going to start typing all the numbers in, 18, 36, 21, 9, and 6. Hit enter after everything and keep on going until I get to the last row. I keep on going all the way through the last row, and again, you do want to make sure you hit enter after the very last number. If you look at that 3 that's highlighted at the end, that's telling me, yeah, I did hit enter there. If I hadn't, it would still say 0 in that space. That's probably the single most common mistake people make, is they forget to hit enter after the very last number. So just make a quick check and make sure, yeah, I did get everything entered correctly. Once we've got the matrix in there again, I want to go to Stat, Tests, chi-square test, make sure it says A and B, which it still does, and go down to Calculate. Again, the thing I care about is the p-value, and here that's 0.0232. That's less than 5%, and so yeah, this time it is a significant result. So yeah, people with different levels of education do tend to have different marital statuses. And here's a third example. This one, it has a much smaller table, so it may be a little bit easier to follow along with this one if you're trying to work it out on your own calculator as we go. It says a college professor kept track of whether students attended or skipped a lecture, and then he gave a pop quiz during the next class and recorded whether they passed or failed the quiz. And he got the results there. You can see among those who attended, 25 passed the test and 6 failed. And among those who skipped, 8 passed the quiz and 15 failed. Now, just looking at those numbers, it looks like way different results depending on whether they were there or not. So I'm going to bet this probably will be a significant result. But we're going to do the test and find out whether it is or not. And it tells us here to do a matrix chi-square test at the 10% level of significance to see if attending the lecture made a significant difference in passing the quiz. So the first step again is enter those numbers in your calculator. And to do that again, we got to get into matrix mode, choose edit, hit enter to choose A. This one is a 2 by 2 matrix, 2 rows and 2 columns. And I'm going to type in those numbers 25, 6, 8, and 15, hitting enter after each one. While you're doing that, I'm going to mention when you get to the problems in your book that are assigned over this, in the problems in the book, they will also have what they call row totals and column totals. You totally ignore those when you're entering the stuff in your calculator. The reason they have those there is if we were reinventing the wheel and making you crank out formulas to get these, you would have to know what those were. But the part of your table rather that matters is just the main ones that fit into the different categories. So here 25, 6, 8, and 15. And now we've got to actually do the test. So of course you want to go to Stat, Tests, chi-square test, and hit enter a few times. And eventually you should get a screen that looks kind of like what I have at the bottom right. This time the p-value is in scientific notation. We've got 6.2971569 e minus 4, which is about 6.297 times 10 to the negative 4th power. So there's 3 decimal places, and the 6 is the 4th place after the decimal. Anytime that you see scientific notation, that's your dead giveaway that this is a tiny, tiny number, and it's automatically going to be significant. Here, it's way less than 1%, and so yeah, we do have a significant result. Going to class actually did help those people with the quiz. And again, your basic steps on a matrix chi-square test. You've first of all got to enter your table in matrix mode in your calculator. And then once you've got it in there, you go to chi-square in the test menu and find the p-value. That's the basic idea for doing a matrix chi-square test. The other test I want to talk about today, which you need to understand but don't necessarily have to do, is what I call a categorical chi-square test. Your book actually calls it a goodness of fit test, and that's actually why on the TI-84 it says GOF, it stands for goodness of fit. What you're looking at in a categorical or goodness of fit test is whether the distribution of data in different categories is different from what you'd expect. Instead of comparing like whether people attended a lecture or didn't, I'm looking at the overall number who passed and the overall number who didn't and seeing is that different from what it normally should be. Some examples of how people do use this. Sometimes, again, I've had people do projects with colors of candy, and a real typical thing here would be, are the colors of M&Ms different from what the company says they should be? Or are they different from what just a random distribution of colors would give you? Is the racial distribution in a community different than it used to be? There's actually a problem in your book that is precisely that question. If you roll dice, are the numbers evenly distributed? I had someone who literally did that for their project one year. They wanted to find out whether their dice were fair, and it turned out, yeah, they were. So what you're doing in each of these is you're looking at what should happen, and you look at what actually is in your sample, and you want to see, is this sample different from the way it's supposed to be? Now, I'm not going to ask you about hypotheses in a chi-square test, but the basic idea of them is that the alternative hypothesis, the one that would be saying it is significant, that would be that your distribution is way different from what it's supposed to be. It's significantly different than expected. On the other hand, the null hypothesis would be it's not a whole lot different from what you'd expect. It could have just happened by chance. You do need to understand the key ideas that go into a categorical or goodness of fit test, but you're not going to actually have to crank out the math for doing them. And the reason why you're not going to have to do the math is that whether it's easy to do or not depends on whether you have a TI-83 or 84. That GOF test is built into a TI-84, but it's not there at all on an 83. And if you wanted to do it with an 83, you'd have to find a different alternative. Either I would have to teach you the formula that calculates this, which isn't that hard, but it's just a pain. Or you'd find some other alternatives, like there's several websites that will calculate goodness of fit tests as well. But I'm going to show you how the TI-84 works, but mostly what you're going to do is just understand how to interpret the final number. So if you do have an 84 and you're trying to do a test like this, you'd go into Stat, Edit, you'd type the observed numbers into L1 and the expected numbers into L2. You remember we did something really similar to that back in the last chapter when we were calculating R. You had like your X's in L1 and your Y's in L2, and it's really the same kind of thing here. Now, one thing I will caution you on, another part of the reason that I'm not going to actually make you do this test unless you have to for your project, is that the problems in the book, they actually present things in the opposite order from what I have here. And again, the expected ones, which is like what it's supposed to be, actually go in the second column. You need to be careful of where that would go. But you type all your numbers into your lists and then you hit quit. And again, you go to Stat, Tests, and here what you'd want to do is choose choice D on a TI-84, which is the goodness of fit test. The input screen in there will say observed and expected, and those should say, and almost certainly do, L1 and L2. If for some reason they didn't, the place that you change that is by hitting second 1 and second 2. That gives you L1 and L2. Something I do want everybody to be able to do is to figure out how many degrees of freedom there are in one of these problems. And degrees of freedom, which is the next line DF on the input screen, it's one less than the number of categories that you have. For example, if you were looking at colors of M&Ms and there were 6 colors you could choose from, 6 minus 1 would give me 5 degrees of freedom. On the other hand, if I had 5 colors of Skittles, there'd only be 4 degrees of freedom. It's always one less than how many categories there are. We're going to look at a couple of examples and I'll show you the things you do and don't have to do with these. So our first example, it says you think your friend is cheating at cards. So you keep track of which suit all the cards that are played in a hand are. And it turns out we got 4 diamonds, 2 hearts, 13 clubs, and 1 spade. And if I was playing any card game and my friend had 13 clubs, that would probably give me a bet that he might be cheating. Normally you would expect that about 25% of the cards should be each suit. And in this case, we were obviously really heavy on one suit and light on the others. And our question is, at the 0.01 level of significance, is this significantly different than should be expected? So the next step here, and it's the next thing I do want you to be able to do, is you want to figure out what are the expected values for your problem. That means how many diamonds, hearts, clubs, and spades would I normally get if everything was just randomly distributed? Well, 25% of things should be of each suit, and since I had a total of 20 cards, a fourth of 20 is 5, that's why I've got 5, 5, 5, and 5 entered on all those things in L2. You're going to see both when you look at your assignment and when you get to the next test, there will be some questions where I do want you to be able to figure out what are those different expected numbers for like each category of your problem. And again, here it's just 25% times 20 all 4 times. So if you had a TI-84, this would be the place you would go to chi-square GOF test. This is something you don't have to do, but there is one small part of what you see on these screens I do want you to be able to do, and that's figure out the degrees of freedom. The degrees of freedom, again, is the number of categories minus 1. We had 4 suits of cards. 4 minus 1 in this problem would be 3 degrees of freedom. So 3 is what you do want to know for the degrees of freedom here. I actually here put 2 different screenshots, and that's because exactly what you would see if you had an 84 looks a little bit different depending on how new of an 84 you have, but everything except that color line is basically the same. This is what the results screen looks like. If I were asking this question like on a test or quiz, what I would do at this point is I would tell you the p-value is 0.0004. And then I would ask you the question, yes or no, is this a significant result? Well, again, what I do to make that happen is I look at that p-value, I compare it to the alpha that was given back at the beginning of the problem, which was 1%. This is definitely less than that, so it is significant. Yeah, your friend really is a cheater. We'll go through another problem real quickly. Again, the 3 things you want to be able to do are figure out the number of degrees of freedom, what would be the expected values, and finally you want to be able to, if you're given the p-value, tell me whether it's significant or not. So this time it says teacher wants different types of work to count for different amounts in the final grade, and we've got what those percentages are. When you actually look at the total points that went into each category, they end up a little bit different from what it said, but we've got some numbers for each of those. These would be the observed or actual values. The percents would be what I'd use to get the expected ones. And the question says, was the point distribution significantly different than the teacher said it would be? And we're supposed to use alpha equals 0.05. So again, the first thing I want you to be able to do is to figure out those expected values. And what you want to do is realize that we had 730 points possible. That was earlier in the problem given to you. And what you would do is take each of those percents times 730. What I actually did when I was working out this problem is I typed in 0.25 times 730 because the first category was 25%. Then 0.5 times 730, 0.15 times 730, 0.1 times 730. Take each of the percents as a decimal times the total, and that's what gives you those expected values. Two other things you want to be able to do. Again, you want to know how many degrees of freedom there are. Here there are 3 degrees of freedom because there were 4 categories and 4 minus 1 is 3. And if I told you that the p-value is 0.61414, you want to be able to tell me, yes or no, is this significant? In this case, this is way more than 0.05, so no, it's not significant. It's really pretty close to what the teacher said it was supposed to be. And again, you want to be able to find on these problems the degrees of freedom, how many categories minus 1, the expected values, which is just each percent times the total, and interpreting the p-value, you want it to be less than the level of significance. So what we just did is we looked at 2 different types of chi-square tests. And it turns out there are tons more that we possibly could do. Your book actually goes into a 3rd type, and there's about half a dozen others we could do. Most chi-square tests, besides the ones we looked at, tend to be used in the field of quality control, in figuring out whether things are spread out too far and need to be changed. It turns out that much of modern quality control theory was developed by a guy from Iowa, a guy named Edwards Deming, who happened to come from Carroll, Iowa. And Edwards Deming was commissioned by the Truman administration right after World War II to help Japan recover after they had been bombed at the end of the war. Japan at the time, its economy was in a complete shambles with very little industry, very little that was going right in that country. And his goal was to rebuild the industrial base of Japan. And what he did is he helped the industries succeed by having them keep track of statistics. And companies like Mitsubishi and Panasonic and Sony and Toyota, all kinds of big companies that you've heard of these days, they adopted those, and that's how they became big successful companies. Today, almost every country in the world and almost every industry in the world uses some form of statistics when they're working with quality control, but most of it was developed by Edwards Deming, who again came from Carroll, Iowa. You don't need to know the part about Edwards Deming at the end, but you do need to know the 2 types of chi-square tests that we talked about. You want to be able to do all the different steps of a matrix chi-square test, and you want to be able to do the parts I talked about with those categorical tests. You'll have some ways that you can practice that with a worksheet that actually is just problems from your book that's online. And of course, next week you'll have a quiz, and there'll be more questions about chi-square when we get to the final test. I am going to mention that when you get ready to take both this week's quiz and next week's quiz, we're going to do things just a little bit differently. Instead of posting that link online, because I had a couple of issues with the test last week, when you're ready to take the quiz, you need to let me know that. Either contact me through Canvas or shoot me an email, and then I'll send you the link to take the quiz. And, it won't be just public online. You need to actually request it, and then I'll let you have that. So that is it for this week. Take care and have a good week.